Hi there and welcome to Olagold Academy. For today's video lesson, we're considering a topic which is elastic properties of a solid. Elastic properties of a solid is a topic under physics. So for this topic, we'll be considering elasticity. We're considering elasticity. We're considering elasticity. Now, what is elasticity? Elasticity is the ability of a solid material to regain its original shape and size after it has been distorted by a force. Alright, it's the ability of a solid material to regain its original shape and size after it has been distorted by a force. Alright, I mentioned distorted. So what does distortion means? Distortion just means to change the size and shape of a particular material either by increasing it or by decreasing it. So if you have a rubber band and you stretch it, it's either you increase it, and in most cases for a rubber band is most in most cases it is the elastic properties is shown by increasing the size, or let me say the distortion is shown by increasing the size. But in the case where you have a spring, you can either reduce the size of the spring or you can increase the size of the spring. So the distortion for the spring can come in terms of maybe you are decreasing the size or you are increasing the size. So that is distortion. Alright, there's one thing I want you to also take note of, that not all solids are elastic, or let me say not all solids possess elastic ability or property. Some solids are elastic, some are not elastic. Example of elastic solids, we have spring, we have rubber band, and other examples. Example of non-elastic solids, we have wood, we have glass, and other examples. Another example of an elastic solid is plastic. Plastic are also elastic. They're also elastic. So solids like glass, solids like metal, solids like wood are not elastic. So that is the concept about elasticity. Alright, so from elasticity, be considering a law known as Hooke's law. Hooke's law. Be considering Hooke's Hooke's law. Hooke's law. Alright, this law was proposed by Robert Hooks. And this law states that provided that the elastic limit of a material has not been exceeded, the extension produced in an elastic material is directly proportional to the applied force. So that is what Robert Hooks says or stated in his law. Alright, that is about Hooke's law. It states that provided that the elastic limit of a material has not been exceeded, the extension produced in an elastic material is directly proportional to the applied force. The force can be an applied mass, can be an applied load, or can come in terms of like force, or when you apply a mass. Alright, a good explanation of the law is with the use of a diagram where we have this. We have a spring having its original size, Let me put the spring as this. So we have the spring as this. So let's call here A. So we have another spring where we attach a mass to. So let's call here B. We have this. So we attach a mass. We have this. So we have this. We have this. All right. So here a mass is being attached. A mass is being attached. Let's say we have another case. Another case where we have a spring with a bigger mass being applied. A bigger mass being applied. Bigger mass being applied. So we have this. All right, we have this. So right here we have a bigger mass being applied. Bigger mass being applied. So we have this. So right here is the original length of the elastic material. Here is the length of the material. You have the length of the material. Right here we have the original length of the material. So here, from here to here is the extension of the material. Let's call here E1. Let's call this mass here mass M1 here. All right. So for the third case, where we have a bigger mass, from here to here is the original length of the spring. This is the original length of the spring. From here to here is the extension. So we have this as the extension. So we have this. Let's call here M2. M2. So we have this. So this explains what Robert Hooke stated in his law. It says that the extension produced in an elastic material is directly proportional to the applied force. Alright, so with this diagram here, we have a spring having this original length, and when we apply mass, a smaller mass, it extends. So we have the extension. The extension also is a kind of length, but it's an extended length from the original length. So we apply a smaller mass, we have this extension. When we apply a bigger mass, we have more extension. So the more the force, the more the extension. The more the mass you apply, or the more the load you apply, the more the extension. So we can say that Robert Hooke says that the extension produced in an elastic material is directly proportional to the applied force. But normally, writing the proportionality, like how they are related, it is not very written like this, because force has to be applied first before there can be an extension. So following Robert Hooke's law, line by line, we should have this, but in physics time or scientifically, there will be no extension without a force being applied. So we have a force being applied first before there can be an extension. So write F before the E. And doesn't end here. We need to remove this sign of proportion. So to remove this sign of proportion, we need to introduce constant. So we have F equal to KE, where K can be the stiffness of a spring, K can be spring constant, K can be force constant, depending on how the question appears. So our decay here is the constant here. So we have this. So we have this as what Hooke's law is saying. From Hooke's law, from Hooke's law, from Hooke's law, we have this. From Hooke's law, we have this. All right. One more thing. Let's make the subject of the formula. So we're going to have over E over E. E cancels this. So we have K equal to F over E. So we have this. We have this. All right. Now let's derive the SI units for this equation here. Now force is measured in Newton, as we all know. An extension is a kind of length, so it will be in meters. So you have meter here. So the SI unit becomes Newton per meter, or we have this Newton per meter. We have this. We have this from Hooke's law. All right, that is that about Hooke's law. All right, right now we're considering some exercises, some calculations on Hooke's law. All right, question 1 now. Question 1 says that a force of 0.8 Newton stretches an elastic spring by 2 centimeters. Find the elastic constant of the spring. And that is question 1. And as usual, our first task is to always list out the given parameters. So given from the question, we are given force as 0.8 Newton. We're also given extension to be 2 centimeters. The extension there is 2 centimeters. It says stretches an elastic spring by 2 centimeters. So the extension is 2 centimeters. So we have the extension as 2 centimeters. And remember, we need to convert centimeters to meters. And that will be 2 times 10 raised power minus 2 meters. So this over 100 will give us this. So to convert from centimeter to meter, we need to divide it by 100. So we have this. All right. From this, let's now bring out our formula. Recall that our K equal to F over E. So we have this. We also calculate our elastic constant. So K equal to question mark. So we have this. All right. So K equal to force is 0.8 Newton. Extension is 2 multiplied by 10 raised power minus 2. So we have this. And final answer, we divide this. Our force constant or our elastic constant becomes 40 Newton per meter. 40 Newton per meter. So we have this as our final answer. We have this as our final answer. All right. Question 2 now. Question 2 says that a force of 2 Newton stretches an elastic material by 30 millimeters. What additional force we stretch the material by 35 millimeter. Assume that the elastic limit is not exceeded. All right, as usual, let's list out our given parameters. The question says that a force of 2 Newton, so we have a force of 2 Newton stretches an elastic material by 30 millimeter. So we have our extension to be 30 millimeter. So we have this. The question says, what additional force? So another F is question mark. What additional force will stretch the material by 35 millimeter? So we're having another extension here to be 35 millimeter. All right, from here now, the question says that a force of 2 Newton stretches an elastic material by 30 millimeter. So it means this force here, which is 2 Newton, stretches an elastic material with an extension of 30 millimeter. So the question says that what additional force will now be needed to stretch the material from 30 to 35. That is our task here. All right. So this becomes our F1 and this becomes our E1. The second force becomes F2 and the second extension becomes the E2. All right. My best formula to make use of when it comes to questions like this that has to do with 1 and 2, like F1, E1. All right. My best formula to make use of is to bring it in terms of those gas laws. Where we have, for example, where we have Boyle's law as P1 V1 equals to P2 V2. All right. Let's say we can derive the formula for this. We are told that force is directly proportional to extension, and force equal to elastic constant multiplied by extension. All right, so both sides over extension to make this constant to stand alone. So we have this. So K equal to F over E. So we have this. So on the account of 2 force and 2 extension, I would suggest that this formula is one of the easier method to get our answer. So we're going to have our F1 over E1 to be equal to F2 over E2. So we have this. Remember, we're looking for F2. So what do? We make F2 to stand alone by cross multiplying. So if I bring this one here and bring this one here, I'm going to have F2 multiplied by F2 multiplied by E1 to be equal to F1 multiplied by E2. So both sides by E1 and E1. E1 cancels E1. So I'm going to have F2 to be equal to F1 E1 over F1 E2 over E1. So we have F2 equal to, now let's begin our parameters. My F1 is 2 Newton, so I have 2 multiplied by my E2 is, remember, there is this for conversion here. But if that, since they're the same, since they're having the same units, there is no need for conversion. But let's just convert to meters. If you convert this millimeter to meter, if you convert from millimeter to meter, we are going to have 30 over 1000. So 0 cancels 0, we are going to have 0.03 meters. So we have this in meters. For 35 millimeter, that will be 35 over 1000. So it becomes 0.035. So we have this. So we are going to have 0.035 meters. So we have this. We have this here. We have this. Alright. So our E2 becomes 0.035 over E1 is 0.03. So our F2 equal to, well, multiply, we are going to get up here, we're going to have 0.07 over 0.03. So we're going to have this. Alright, so when we divide further, F2 now equal to, that will be 2.33 Newton. So we have this. But remember, the question says that what are additional force? So it means that we are going to subtract the first force from the second force. So additional force now equal to F2 minus F1. So we have this. My F2 is 2.33 minus my F1 is 2 Newton. So I have this 2 Newton. If I subtract this, I'm going to get my answer to be equal to 0.33 Newton. So this becomes my final answer. My additional force becomes 0.33 Newton. So I have this. Alright, I'll be doing a second video on this, where I'm going to explain strain, stress, Young modulus. And we're going to look at some few examples on them. So alright, that is all for this video lesson. If you find this video lesson helpful, do also hit the like button, subscribe, comment, and share to people who are in need of knowledge and such. Alright, this is Olagold Academy. Thanks for watching.